You see them absolutely everywhere, right? From the rafters in a house to the graphics in a video game. Triangles. But they almost always come with a puzzle. You know, two sides or maybe a side and an angle, but you need to find that last missing piece. So how do you do it? Not just for one specific type of triangle, but for any triangle you come across. I mean, we've all been there. Staring at a triangle, a few numbers scattered around it, and that one side just labeled X. Now, you could try to memorize a dozen different formulas for a dozen different situations, but honestly, who wants to do that? The real secret isn't memorization. It's about knowing which tool to grab for the right job. So today we're going to build that toolkit piece by piece. We'll start with the hammer of geometry, the tool for simple right triangles. Then we'll get a bit more precise with trigonometry, for when angles get involved. After that, we'll bring in the power tools, the law of sines and the law of cosines, which work on pretty much any triangle. And finally, we'll see how to combine these to solve some really clever puzzles. Let's get into it. Okay, first up, the absolute classic. We have to start with the most familiar shape out there, the right triangle. This is really the bedrock of all triangle geometry, and our first tool is probably one you've heard of.
You know this one. A squared plus b squared equals c squared, the Pythagorean theorem. But, the formula itself isn't the most important part. The real key is knowing when you can use it. You need two things, and only two things: a 90-degree angle and the lengths of any two sides. That's it. And just remember, c is always the hypotenuse. That's the long one, sitting right across from that 90-degree angle.
So let's give it a try. We've got a right triangle. The hypotenuse, our c, is 10. One of the shorter sides is 6. And the missing side is x. So do we have our two conditions? Yep, a right angle and two known sides. This is a job for Pythagoras. Okay, the process is really straightforward. We just plug in what we know. 6 squared plus x squared equals 10 squared. That becomes 36 plus x squared equals 100. A little quick subtraction. We move the 36 over and you get x squared equals 64. Take the square root of 64. And there you have it. X equals 8. But Pythagoras has a weakness. What happens if you don't have two sides to work with? What if all you've got is one side and an angle? Well, for that, we need to add a new set of tools to our kit. It's time for some basic trigonometry. Now, don't let the name scare you off. For right triangles, almost everything you need to know comes down to one fantastic word: SOHCAHTOA. Seriously, it's just a simple way to remember the three main relationships between the angles and the sides. So here's how to think about it. Imagine you're standing on one of the corners of the triangle, one of the sharp ones. From where you're standing, there's one side that's opposite you, way across the triangle. The side right next to you, that's the adjacent side. And of course, the long slanty one is always the hypotenuse. SOHCAHTOA is just a code for this. So means sine is opposite over hypotenuse. Ka means cosine is adjacent over hypotenuse. And toa means tangent is opposite over hypotenuse. Simple as that. Okay, let's put it to the test. Which tool do we use? Imagine we're given a 30-degree angle. The side opposite that angle is our unknown x, and we know the hypotenuse is 50. So what info do we have? We have opposite and hypotenuse. Now look back at our code word. Which part of SOHCAHTOA uses O and H?
That's right, it's SO, which stands for sine. So we just set up our equation. Sine of 30 degrees equals the opposite side, x, divided by the hypotenuse, 50. Now you just grab a calculator and hey, quick tip, make sure it's in degree mode, and you'll find that the sine of 30 is exactly 0.5. A little multiplication, and boom, we find that x equals 25.
So far, so good, right? But all of our tools so far have had one big limitation. They only work on right triangles. What about all the other triangles in the universe? For this, we need to bring out the heavy-duty equipment, the law of sines and the law of cosines. First up is the law of sines, and it sets up this really beautiful, simple proportion between the sine of an angle and the length of the side opposite it. This is your go-to tool when you have what I like to call a matching pair, meaning you know an angle and you also know the side that's directly across from it, plus one other piece of information. And next, we have the law of cosines. If you look at it closely, it should seem kind of familiar. It starts with c squared equals a squared plus b squared. Hey, that's just the Pythagorean theorem. But it has that extra bit tagged on the end. Think of that as the correction factor for any triangle that isn't a perfect right triangle. In fact, if your angle C was 90 degrees, the cosine of 90 is 0, and that whole last term would just disappear, leaving you with good old Pythagoras. This is basically the Pythagorean theorem upgraded. So how do you choose which one to use? Well, it's actually pretty simple. You look for a matching pair, an angle, and the side directly opposite it. If you have a pair like that, you're going to use the law of sines. If you don't, but you do have two sides and the angle that's sandwiched right between them, then you need the law of cosines. All right, we have built the core of our toolkit. We've got Pythagoras, SOHCAHTOA, and the laws. Now let's look at a couple of trickier puzzles where we might need to combine our tools or maybe, just maybe, find an elegant shortcut. Take a look at this. It's kind of like a triangle inside of another triangle. We have two unknowns here, x and y. Now, to solve this, you typically need to use our SOHCAHTOA tools twice, once for that little triangle on the right and once for the big one overall. This would give you two separate equations, and then you'd have to solve them together. It's a great example of combining our tools to get the job done. Okay, now for a really interesting one. We've got a big right triangle, and we've dropped a line, that's the altitude, straight down to the hypotenuse. This splits that bottom line into two pieces with lengths 8 and 32. Our goal is to find the length of that altitude, x. How would you even begin with this one? Well, the long way is, frankly, a nightmare. You've actually got three right triangles all packed into this one shape. The small one on the left, the medium one on the right, and the big one overall. You'd have to write out three separate Pythagorean equations and then weed through this swamp of algebra to solve them all together. I mean, it works, but there has to be a better way. And you know what's way better than a swamp of algebra? A beautiful, elegant shortcut. Turns out there's a special tool in our toolkit that's built for exactly this situation. It's called the geometric mean theorem, and it is one of the coolest shortcuts in all of geometry. All it says is that the length of that altitude, x, is simply the geometric mean of the two pieces it splits the hypotenuse into. In other words, you just multiply those two pieces together and take the square root. That's it. Seriously. So all of that painful algebra we were just looking at, forget it. It just boils down to this. We plug in our numbers. X is the square root of 8 times 32. Well, 8 times 32 is 256. The square root of 256 is 16. Done. A problem that looked like it would take a page of work is solved in a single line. That is the power of choosing the right tool. And here it is, our complete toolkit, all in one place. This is basically your decision guide. Whatever triangle puzzle you're facing, just find your situation on the left and grab the tool on the right. Got a right triangle with two sides? Pythagoras. Any old triangle, but you got that sandwiched angle? Law of cosines. That really specific altitude setup? The geometric mean shortcut. It's all right here. So, we've put together this really powerful set of tools, from the ancient theorem of Pythagoras all the way to the slick shortcut of the geometric mean. The real question is, now that you know how to look at a problem and choose the right tool for the job, what other geometric puzzles, what other real-world problems can you start to unlock?